In this video, we are going to talk about the orthogonal projection. We've already talked about the dot product. And so if you need to, if you haven't watched that video about the definition of the dot product, you need to go back and watch that before this one. Okay, so about the orthogonal projection, say we have two vectors, u and v. Okay, to get the orthogonal projection of u onto v, then what we're going to do is drop a perpendicular from the tip of u down to the vector v. All right, and that's indicated by this little dotted line right here. That little dotted line is going to make a right angle with the vector v. Okay, so we're going to draw that down. And then we're going to make a new vector. That vector is going to go from the tail of u out to that point of intersection of that perpendicular. So here the vector is shown in red, like this. All right, and that vector is the orthogonal projection of u onto v. Okay. You can kind of think of it as how much what part of u, right, is kind of points in the direction of v there. Okay. So that's what the orthogonal projection is in terms of geometry, right? And you can see where it got its name from. Orthogonal, right, it means perpendicular, right, roughly. And then we're projecting, right, this vector onto the vector v, like so. Okay, so that is what the orthogonal projection is. And in that picture that I showed you, the angle between the vectors u and v was an acute angle, but there's a couple of other cases, right? The vector between u and v could be a right angle already, like this. And so when you do the orthogonal projection, right, when you drop that perpendicular, it's going to coincide with the vector u. And so when you draw a vector from the tip of u out to where that perpendicular hits v, well, that's the same point. So if you have the same terminal and initial point for a vector, that's just the zero vector when you do that. So really, you get the zero vector if they're right angles. And remember, we talked about the fact that the dot product, right, of two vectors that were where the angle was pi over 2, a right angle, is 0. So that's connected to that idea. And then the angle between the vectors u and v can be obtuse, so greater than 90 degrees. And so in that case, you'll have to kind of extend the vector backwards a little bit. So there's a dotted line under here that you can't see. The vector v would start here, and then I drop the perpendicular down here. And you can see that the orthogonal projection is kind of pointing in the opposite direction as v in this case. Okay. So the red vector would be the orthogonal projection. So it's kind of the same. The main difference is that the orthogonal projection is going to be pointing in the opposite direction of the vector v that you're projecting onto. Okay. All right, so that brings us to the geometric interpretation of the dot product, right? And so first off, right, the magnitude or the absolute value of the dot product. When I take the dot product of two vectors, right, the absolute value of it. Remember, the dot product is a scalar, so we're in this case just talking about the absolute value. It's the product of the magnitude of the orthogonal projection of u onto v and the magnitude of v. All right, I have a typo in here. This needs to go out. So that's the absolute value of the number that you get when you do the dot product. And I'll show you in a minute on this Desmos demonstration. Okay, and so then it comes to the sign of the dot product. If the angle between u and v is acute, then the sign of the dot product is going to be a positive number. Okay, just like we saw in this situation here, if the angle between u and v is an acute angle, then the orthogonal projection is going to be pointing in the same direction as v, like that. If the angle between vector u and vector v is a right angle, then the dot product of the two vectors is going to be 0, which we already saw. If the angle between u and v is obtuse, then the sign of the dot product is going to be negative, like this over here. Oops. Like this situation. Okay. Okay, so let's take a look at this Desmos demonstration that I have. All right, and in this demonstration, I just tried to make it fairly easy to code in here. So you can adjust these vectors by dragging these points. Like so. I only did whole numbers, again, to make the math a little bit easier to do in your head. But that doesn't mean they have to be whole numbers, right, in here. Here I have the vector u, and the vector v is the red vector. And then the orthogonal projection is going to be this green vector right here, okay? And down here I calculate the dot product. So here you can see that the dot product is 12 in this case for these two vectors, all right? So this vector u, right, if I take the projection in the direction of v, I can see that the magnitude, right, of that projection is 2, right? This green line segment has length 2. So I also force this to be on the x-axis to make that a little bit easier to get the magnitude so we could just see it. So the green vector has magnitude 2. The red vector has magnitude 6. And so 2 times 6 is 12. And now let's see, I can make it a little easier to, if I turn the green one off and on, there's the red one. So you can see the red one, the red vector in this is always going to be at the start at 0, 0 right here, and extend out to whatever this point is, and 6, 0 in this case. Okay. All right, and as you can see, if I start moving these around, I'm going to move this one to, let's see if I can, yeah. I'm going to move this one to here, and I'm going to make this one a little bit bigger. All right, so here in this case, where we have the vector u, the orthogonal projection, right, goes from 0 to 4, so it has length 4. And in this case, the vector that I'm projecting on goes from 0 to 7, so it has length 7. So 7 times 4 is 28. That's the dot product here. Let me move this one back a little bit. All right, here it's hard to see the red vector, the vector that we're projecting on, but 0 to v, 0 to 2 is what v is, so it has length 2. And in this case, the projection has the orthogonal projection of u onto v has length 4. So the dot product of those two vectors is 4 times 2. Let's see, if I make it the two vectors perpendicular to each other, you can see the dot product is 0, right? Because the projection, actually my green vector, it's not really drawn it correctly. It should just be the 0 vector right here. So that's not quite right. I'd have to go back in and alter the code to get it to do that correctly. And now let's see if I put the vector u over here so that it makes an obtuse angle with v. You can see now the projection over here is still length, it has length 2, the orthogonal projection does. The vector v, right, has length 2. And so you can see that the absolute value of the dot product is the product of their lengths, 2 times 2. But now the sign of the dot product is negative because of the fact that the angle is obtuse in between there. So that's what the dot product is. It is the product, right, of the length of the orthogonal projection and the vector that you're projecting on with the signs thrown in there, right? Acute angle is positive. If it's a right angle, it's the dot product is going to be 0. If the angle between the two vectors is obtuse, right, then the dot product is going to be a negative number there. All right. So geometrically speaking, that's one way to look at the dot product. Okay, so we're going to leave it at that in this video. In the next video, we're going to talk about a much easier formula for computing the dot product.